Hello, I'm Dr. Harper. This video is an operations management. It's a lecture video on scheduling. So let's bring up the notes. In scheduling, the input-output process could be the supplier coming into the process, going through the customer. I can overlay a logistics model over this input-output process. And the logistics model simply means movement of things. And so you have the production control in the middle, where you're controlling production and moving inventory and items through your production facility. But upstream, you're going to have a purchasing operation and then a receiving operation to receive the products in, or the inventory or subcomponents or products into your operations unit, distribution down to demand management. So depending on where you are, the logistics model could be in 5 or 6 and even more different stages. Today, in this lecture, we'll be looking at production control. I'll be dividing this up into 3 different sections. Job shop scheduling, which I'll look at sequencing rules, flow diagnostics, Johnson's rule, and Gantt charts. That's the subject of this video. Another video would be assembly line, aggregate runout method, and service design, cyclical scheduling. So we will go through these 4 different steps, these 4 different areas today in the under job shop. Remember, the job shop is a process-focused design, assembly line is a product-focused design, and a service design is under service definitions. Okay, let's look at sequencing rules. Here's the idea and setup for sequencing rules. You have something called a queuing system. A queuing system is made up of a queue, and this queue is just a waiting line. It's a waiting line of entities. It could be people, it could be jobs, it could be calls coming into a switchboard, and the server is servicing those items waiting in the queue. As I said, this could be people waiting in line at the teller of a bank. These could be jobs waiting to be processed by a company. These could be calls coming into a switchboard. So a queuing system is you have entities arriving at the queuing system, entering the queue, and then being processed through the server and then leaving the system. Okay, so that's the setup. So if you have a number of jobs, let's say jobs to be done in this queuing system, then to be processed through the server, and they're in line, they're in a queue, then the idea here is that if you can sequence that queue, if you can move them around and create a different order according to a rule, that sequence is essentially your schedule. And so a sequencing rule is a rule you follow to create a sequence which will be your schedule, which will go through the server. So the way I've set this graph up, this is the first job, then the second job, then the third job, then the fourth job. Okay? So we will look at 5 different sequencing rules, and here they are. And these sequencing rules will follow the rules, will create a sequence, which is our schedule, and these rules will have different characteristics, which I'll mention. Okay, so let's bring this down here. Let's look at some examples. First, let's assume we have 4 jobs, A, B, C, D, and along with each one of these jobs come a processing time. Now, PT is processing time. Now, processing time, let's use a unit of days. So job A takes 4 days to be processed through the server, and it's waiting in line. Okay, B takes 6 days, C takes 10 days, and D takes 18 days. Okay, the minimum processing time rule simply says the job with a minimum processing time will be the first job in the schedule. So A will be first because the 4 is the lowest, is the minimum processing time. Then B is the next highest, which is the second job. C is the third job, and then D is the fourth job. And that's really all there is to the minimum processing time. You just place the order. You place them in order. First, second, and third, fourth, A, B, C, D. And that's really all there is to it. The second is the earliest due date. Along with the processing times, each job also comes with a due date. So let's assume this due date, these are dates, but they're numbers, but these dates are from a Julian calendar. A lot of people are used to a Gregorian calendar where we have January, February, March, April, May, the months and different days within a month. But a Julian calendar takes let's say a Gregorian calendar, and there are other calendars like a Roman calendar or Greek calendar, Orthodox calendar, but we're assuming a Gregorian calendar, and they sequentially numbers the jobs and just ignore the months, and those are called Julian dates. So this is a Julian date 63. Now on a Gregorian calendar, January has 31 days. If it's not leap year, then February has 28 days. Well, 31 and 28 then is 59. So date 63 would be the fourth day in March, March 4th. Okay, so that's how you convert back and forth between Julian calendar and Gregorian calendar, depending on whether it's leap year or not. Okay, so these are the dates. Now the earliest due date simply says the one with the earliest date, and the minimum time here is 51. That's the first job in the schedule. The next highest date is 60 here, so that's going to be the second job in the schedule. The next highest time is 63, that's the third job, and then 66 is the fourth job. So you just order them according to the due date. The earliest due date first. Now, if all the processing times are the same, the due dates are different, you may want to use the early due date. If all the due dates are the same and the processing times are different, then you may want to use the minimum processing time, and that's when you would use these. Now, the third one, the minimum start date, combines the processing time and due date together. They take the due date and minus the processing time. So 63 minus 4, the start date is 59. 51 minus 6, the start date is 45. Now, the interpretation of the start date simply is, well, if I subtract the processing time from the due date, that is a date, that date is the processing time before the due date. So if you start right on that date, then you'll be done right on the due date. So the start date is the date on which you start a job to be done right on the due date. So if you start the job before the due date, you'll be early. If you start the job after the due date, you'll be late. If you start the job on the due date, you'll be right on time. Okay, the minimum start date simply says, okay, which is the minimum start date? Let's say 45. So that's going to be my first job in my schedule. The next highest start date is 48. That's my second job. 50 is my third job. 59 is my fourth. So there's my schedule. The minimum start date would be B, D, C, and A. And so the minimum start date will be used if you want to combine these two together. And so when you have different processing times, different due dates, taking both of those into account, you'll have something called a minimum start date. Now the third one is related to the minimum start date, called the minimum slack time. Now I'm introducing this for a number of reasons. First of all, it is you take the start date. Notice you come back to the start date and you subtract something called the present date. Okay, let me define the present date. The present date simply is when all these jobs begin arriving at the system, they'll queue up. Then you use your sequencing rule and to order them. And then when you start processing, that's defined as the present date. It's the present date on which you start processing this project. Okay, so the present date is date 53. So that's back in February. So date 53, you say, I'm going to start processing these jobs. I'm going to subtract the present date, 53, from all the start dates. Well, since I'm subtracting the same number from all the start dates, then the order in which I have my slack time will be in the same order, will be similar to the start date. So the schedule will be the same, the first, second, third, and fourth. But the slack time definition is why I'm introducing the minimum slack time, because the slack time can be used for analysis, whereas the start date is used for scheduling. But I introduce it here, and the slack time becomes very important when you have more complex systems, more complex than just a single queue and a single server. We won't get into those in this lecture, but I'm introducing it here. So the idea of slack time is, well, if I subtract the present date from the start date, well, notice it's going to be 6 days, which is 6 days before my present date is 6 days before my start date. So if I start on the present date, I'll be 6 days early. Well, if I start on the present date of 53 back in February, well, the job B will be 8 days late because it's minus. C is 3 days late, D is 5 days late. And so we're looking at the schedule here and saying, oh, this gives you a lot of information about the schedule, or these jobs. And that is, the only job that will not be late will be A. Because you can't start all the jobs on the same, you can't start all the jobs together. You can only start them one at a time. Well, any of these jobs, if you start, they'll all be late. This one will be early. So the only job that will be early or on time is A. All the other 3 jobs are going to be late no matter when you start them, because the present date is when you start. So this is a terrible schedule. They're all going to be late. So I introduce this just to show you all the different types of possibilities on the start date and slack time. The last one is the critical ratio, the minimum critical ratio. Now I define the critical ratio as the due date minus the present date divided by the processing time. So it is a ratio. You could say critical index, but I'm calling it a ratio because the ratio could have a number, could be defined differently. Okay, first of all, the numerator, the due date minus the present date. Well, if you look at job A here, the due date, the present date is 50. The due date minus the present date, 63 minus 53 is 10. Divide by the processing time is 4. So 10 over 4 is 2.5. So that's for the job A. Well, let's interpret the critical ratio. So the numerator is called the supply time because the due date is when it's due. The present date is the present date. So between today, the present date, and the due date in the future, that difference is the time supplied to do the job. So if you take the time supplied to do this job between today and when it's due, divide by the processing time, that ratio gives you a lot of information. In other words, if the processing time as of today is less than the supply time, the ratio is greater than 1. So therefore, you'll be early because the processing time is less than the supply time. And so you'll have a slack time of 6, actually. If the processing time is greater than the supply time, if the supply time is greater than the processing time, okay, if you're supplied, let's say you're supplied 1 day to do this job, but the processing time is 3 days, you're going to be late. That means the ratio is going to be less than 1 down here. So when the critical ratio is less than 1, between 0 and 1, then you're going to be late if you start today. Now, notice that for job B, the due date is 51, the present date is 53. Okay, so on the present date of 53, the due date was 2 days ago. So you're already late before you even start. Well, that's a negative critical ratio. A negative critical ratio means you're already late before you even start. So there's a lot of interpretations here on the critical ratio. Well, to schedule it, you take the lowest one first, then the next highest one, then the next highest one, then the highest. Well, the reason I introduce critical ratio is because this ratio, you can have different types of ratios. And so the critical ratio is the most flexible, and therefore I consider it the most powerful critical ratio, because you can use the critical ratio all different ways, depending on what type of objective you have in your schedule. We won't get into that, but that's an introduction. Okay, now here's our schedules. We have these schedules here. Let's analyze them. A very popular metric to analyze them is called the flow diagnostic. So the flow of a job is the number of days a job is in the system. Okay, so the system is made up of a queue and a server. So if a job spends 1 day in the queue and 2 days in the server, the flow is 3. Okay, so the flow time is how long it spends in the system. So it's how long it spends in the queue plus how long it spends in the server. You add those two together. So let's look at the flow time of every job in the MPT schedule. Well, first of all, A is the first job in the schedule. Well, since it's, let me reduce this down, we can see it. So since A is the first job in the schedule, then there is no queue time. Because on the present date, if it's the first job, it's not going to wait, it goes right into the server. So the first job in any schedule will have no queue time. But the processing time is 4. So 0 time in the queue, 4 days in the server, the flow is 4. Now B spends 6 days in the server. But B is behind A. That's the second job. Since B is behind A, it has to wait until A is finished on the server and leaves the system. Well, it's going to take 4 days to do that. So 4 then becomes the queue time of B waiting for A to be finished. So the queue time is 4. The processing time is 6. So 4 plus 6 is 10. The flow time is 10. So notice here, the queue time of the first job at any schedule is 0, but the queue time of a job after the first job will be the flow of the preceding job because it's in line. It has to wait for that job to leave the system before it can be serviced. So C has a processing time of 10. It has a queue time of 10, so the flow time then will be 20. D has a processing time of 10, a queue time of 20, so the total flow then is 20 plus 18, which is 38. So there's the flow of every job in this schedule. So at this point, we have two things. We have two characteristics. One, the queue time of the first job of any schedule is 0. The queue time of a job within the schedule is the flow of the preceding job, and the flow of the last job in the schedule is the total processing time, or the time of completion, or the total processing time of this project. So the time it takes for the last job to go through the entire system, in other words, the time it takes the last job to go through the queue and through the server is the time of completion. And that's referred to as the make span. A make span is the same as a total processing time, or the time of completion of the project. That's how long it takes. So notice I can add up the processing times, and that's 38. Okay, so 38 here is the total processing time. That's the same as the flow of the last job in the schedule. So there's some properties here. Now this is the flow of every job in the schedule. I can add up the flow, and this is called the flow of the schedule. So we have a flow of a job in a schedule, and we have the flow of the schedule. So I can bring that down, or I can look at the processing time on, I can do the same thing for the earliest due date, the minimum start date, and minimum slack time, because they're the same schedules, and the minimum critical ratio. But then there's some more properties here. Notice the processing time is 38, 38, 38, and 38. The processing time is the same, regardless of the schedule. Therefore, the schedule, the total processing time is independent of the schedule in an n/1 system. And that's a property. I'll say that again. The total processing time of a schedule in an n/1 system is independent of the schedule. The processing time is independent of the schedule. Why? Because all the processing times are the same. Now look at the flow times. The flow here is 72, 80, 102, 94. The flow time is dependent on the schedule in an n/1 system. Okay, so we have a number of metrics here, a number of diagnostics. The flow of a job in a schedule, the flow of the schedule. We have the total processing time of a schedule. And we have the queue time of the first job and the queue time of any other job, which is the flow of the preceding job. Okay, so we have a lot of properties and diagnostics that we can use here. Well, there's a few more. We can bring this 38 down, the total processing time, and there they are. Bring down the flow. There's a total flow for every schedule, and there they are. Now I can take the total flow here and divide by the number of jobs. And that's the average flow per job. I can take the flow and divide by the total processing time, or the make span, 38. And that's the average jobs per day. So here's two diagnostics, actually three diagnostics, which are dependent on flow. And that's why flow is so important, because a lot of times the average flow per job or the average jobs per day, that is used in describing, in analyzing a schedule, and sometimes in managing a schedule. And so since the flow is a numerator of each one of these, then the minimum total flow, the minimum total flow, the minimum average jobs, average flow per job, and the minimum of the average jobs per day will always be the MPT rule. So the MPT rule will minimize the total flow, average flow per job, and average jobs per day. So there's another property. Okay, closely related to flow is something called lateness of a schedule. How many jobs are late and how much lateness do you have in a schedule? So here's the development. The present date is date 53 from above. See up here, the present date up here is 53, using these same numbers. Okay, now the date of completion is defined as the present date plus the flow. Because remember, the flow of a job in a schedule is how long it spends in the schedule. So if I add the present date to that, the present date plus how many days it's in the schedule, that's going to be the date at which it leaves the system. Now the days late will be the due date minus that date of completion. Because if the date of completion is greater than the due date, well then it's past the due date and it's going to be late. If the date of completion is less than the due date, well it'll be early. And you'll have a negative lateness. So here's the MPT rule. Here's the processing time, here's the flow, the present date. Okay, and then here's the date of completion. I'll just add these two together. Here's a due date, and then the lateness, I'll just take the difference here. Okay, due date minus the date of completion, and there they are. I can add this up, and I'll call that the lateness. Well, we can see here how many days are late. Well, 3 will be late because they're greater than 0. Now notice A has a negative lateness, which means it's going to be early by 6 days. Well, the 6 days early is exactly what my slack time says. Okay, and so the flow will the lateness will also tell you the slack. Well, here's how many days late B, C, and D are going to be. But when I look at the other schedules, these are all late, these are all late, and these are all late. How about that? Interesting. But I can add up all the lateness, and I include my minus 6 here. So it's 44, 52, 74, 66. Well, let's see here. 44 looks like it's the lowest minimum lateness. So lateness will be another diagnostic that we will be looking at. Okay, now let's go to an N by 2 system. An N by 2 system, we have 4 jobs. Now we have 2 servers in series. And by the way, there's a lot of different Johnson rule. This is only one version of the Johnson rule. Since we have 2 servers, I have 2 sets of processing time. Processing time for the first server, processing time for the second server. So now there's some rules here. The rule is once you create your schedule or your sequence, the jobs stay in that order. So when the first job here goes into the first server, well, the second server here is idle. Well, the second job will not get out of line and go to the second server. It stays in line. So we're assuming that all these stay in line, so you can have the server 1 busy and server 2. Both servers could be busy, or server 1 could be busy and server 2 could be idle. Okay, but there's also different rules here, and that is if the first job is serviced by server 1, two things could happen. The first job is done and it moves to the second server, and now the second job, it goes into the first server. So now both servers are operating at the same time. Now two things can happen. Okay, server 2 could be finished before server 1. If that's true, then only server 1 will be busy and server 2 will be idle. The second thing that could happen, that can happen is that server 1 could be finished before server 2. Now, if that's true, then this job will leave server 1, go to server 2, and will have to wait in front of server 2. And then job 3 then will be processed by server 1. Job 1 is still being processed on server 2, and job 2 is in a queue in front of server 2. And job 4 is in a queue in front of server 1. So we're going to have a queue in front of server 1 and a queue in front of server 2. So now we have two servers, well, that means we have two queues. Okay, now before we've established that the processing time, the total processing time in an n-by-1 system here is independent of the schedule, because it's always the same. That's for an n-by-1 system. But for an n-by-2 system, the processing time is dependent on the schedule. So different schedule will give you different processing times. To minimize your processing time, you use a sequencing rule called Johnson's rule. So let's do it. Johnson's rule is a 3-step algorithm. Step 1, first of all, here's a 3-step algorithm down here. The total processing time is independent of a schedule in an n-by-1 queuing system. The total processing time is dependent on a schedule in an n-by-2 queuing system. The sequencing rule to minimize the total processing time in an n-by-2 queuing system is Johnson's rule. So Johnson's rule is a sequencing rule. It's a sequencing rule for an n-by-2 system that will minimize the total processing time. So let's do it. Johnson's rule is a 3-step algorithm, 1, 2, 3. And so let's just do it. Okay, first of all, step 1, you bring down all of these times, all 4 jobs, all 8 times, you bring them down right here, and there they are. Okay, step 1, find the minimum processing time. Well, in all of these, all the times, 4, 3, 2, 6, 4, 1, 5, 4, all 8 times, which one is minimum? Well, the minimum right there is 1. Okay, step 2 says, if the minimum time is on the first server, then schedule the job in the first position. If the minimum time is on the last server, schedule the job in the last position. So notice this minimum time is on server 2 here. It's in the last server. Therefore, schedule C in the last available position, which is the 4th job. Now, if this minimum time had been on the first server, it's not, but if it had, I would have scheduled C in the first available position. But the minimum time is on the second server, the last server of the 2, so I'm scheduling C in the last available position. That's step 2. Step 3 simply says eliminate C and go to step 1 with the 3 remaining jobs and 4 and 6 remaining times. So let's do the algorithm a second time. Of the 6 remaining times, 4, 3, 2, 6, 5, 4, 2 is a minimum. Step 2, 2 is on the first server, therefore schedule B in the first available position. There it is, the first job, B. Step 3, eliminate B, go back to step 1 with the 2 remaining jobs and 4 remaining times which is 4, 3, 5, 4. And let's do it again. Step 1 says, okay, 4, 3, 5, 4, which one is a minimum? 3 is the minimum. 3 occurs on the last server, so I schedule A in the last available position, which is the third job. It's the third in the sequence. I eliminate A. Now I have one job and one space left. I put D in that space. Now the Johnson's rule schedule is BDAC to minimize the total processing time. And that's Johnson's rule. Okay, so now there's 2 things I want to mention before we go on. The first is someone always sees it and say, what if there's a tie here? Well, what if both of those were 3? Well, then which one do you pick? You pick A goes in the first available position or A in the last available position. So which one do you pick? Good question. Well, there's 2 answers to that question for this course. The first answer is, I'll be very careful never to do that. So you have to worry about it. The second answer is not for this course, and that is when you leave here, it does happen where these are the same. Well, that just leads you into a whole different sequence of decisions to choose. For example, one procedure would be, well, arbitrarily pick one. Just pick this one. Create the schedule, go all the way through, get some flow diagnostics. Oh, then go back where you made that decision, do the other one, and pick that one and go all the way through. You're going to get a different schedule. You probably get a different schedule. Take all your schedules and then do some flow diagnostics or some kind of diagnostics, lateness, and which one do you want to pick? And notice that's a lot more work. That's why the first answer is so important. I'll be careful never to do that. I won't do that. I'll make all of these unique. In other words, there's only one answer. In this case, it's BDAC. B is the first job, then DAC. So if I put BDAC in my graph up here, that's B, that's D, and that's A, and that's C. If I'm writing it in a sentence, then it's left to right, B, D, A, C. Okay, so there's Johnson's rule. The second thing I want to point out is the concept that's illustrated here behind Johnson's rule. Okay, first of all, notice the smaller jobs, let me shade this in, the smaller jobs are on the last server. The smaller jobs on the last server here will be later in the schedule. The smaller jobs on the first server will be early in the schedule. Okay, notice this is the fourth job, and this is the first job. So I want to emphasize that. That's why I'm shading this in. I want to emphasize that. That's the concept of Johnson's rule. Now, this concept can be used even though you don't have an n/2 system. When you have things in series that have to be done, well, you'll take the shorter times at the end of the server and just move those to the back of the schedule. Take the shorter times up front, move them to the front of the schedule. So this concept can be used very effectively. And so if you have an n/4 system, n/6 system, n/10 system, and that does happen quite a bit, Johnson's rule can be applied not directly, but the concept can be applied, which implies a heuristic method. A heuristic method using Johnson's rule concept. Now, you won't get an optimal schedule, but you get a very good schedule. In other words, the good schedule could be 90% optimal. It could be as much as 95% optimal. It could be very, very good. So the Johnson's rule concept can be used, even though Johnson's rule does not necessarily apply because of the schedule. It's not an n/2. Okay, the last thing is going to be Gantt charts. Let's look at the Gantt charts. Now, let's take the n/2 system here and the 2 processing times here on the servers, and let's look at 2 schedules. First of all, the FIFO schedule, ABCD, the Johnson rule schedule, BDAC. Now, all a Gantt chart is down here is a timeline it's a timeline, a graphical timeline of the project. All it is a graph over time. So let's take the FIFO schedule here, ABCD, and let's take these numbers right here, bring them down here, and so now let's Gantt this out. Okay, let's use a Gantt chart to Gantt this. So let's just create the Gantt chart. Okay. Okay, first of all, I'm going to let 1 represent the number 1 represent time on server 1. For example, A is a first job in the schedule. It takes 4 days on the first server. So I'm going to represent that with 4 1s. 1, 1, 1, 1. So those 4 1s right there represent 4 days on server number 1. Well, that's what A is going to be. So A is 4 days on server 1. Then it goes to server 2, and server 2 requires 3 days. So we'll have 3, 1, 2, 3. And I'm letting 2 represent a time on server 2. So A spends 4 days on server 1, 3 days on server 2. So on a timeline, I have 4 here and I have 3 here. So the total flow of A is going to be 7 days. And the queue time is 0 because it's the first job in the schedule. So I'm just on a timeline graphically representing A. Okay, now look at B. Now there's going to be some rules here, and the rule is a server can only service 1 job at a time. So B is ready to be serviced for 2 days, but then it can't service because 1 is busy with A. So B has to wait in a queue in front of server 1, waiting for 1 to be done. It's waiting 1, 2, 3, 4 days. Now when server 1 is done, then it can be processed. Then it can process B for 2 days. So I have 2, 1, 2. Now at the end of 2 days on the first server, B moves from server 1 to server 2. And so it looks at server 2, but then server 2 is busy. Server 2 is busy processing A. So now B has to wait in a queue in front of server 2. So that space right there is a queue time in front of server 2. You can't have a server 2 operating 2 jobs at the same time. Therefore, B here has to wait in a queue in front of server 2. Now when server 2 is available, it can process B for 6 days. So I have 6 2s, 1, 2, 3, 4, 5, 6. So now I can see the flow time of B is 13 days. Now remember, the flow is the queue time plus the processing time. Right here, the processing time 6 plus 2 is 8. Well, if the flow is 13 and the processing time is 8, well, 13 minus 8 is 5. The queue time must be 5. Well, it is. It's 4 days in front of the first server, 1 day in front of the second server. 4 plus 1 is 5. Okay, C. Well, C now is going to spend, it has to wait for 1 to be finished on A, 1 to be finished on B. Then it can be processed for 4 days, 1, 2, 3, 4, and there it is. And then when C is finished with on the first server, it moves to the second server. Again, the second server is busy for 3 days here until, so that's queue time that C has in front of the second server. When the second server is available, then it can be processed for 1 day here. So I have 1 day. Now D is 5 days on the first server. It has to wait for the first server to be finished with A, finished with B, finished with C. Then it can be processed for 5 days. 1, 2, 3, 4, 5. And there we go. Now when D is finished on the first server, it goes to the second server. Well, the second server is available. As a matter of fact, it's been idle for 1 day. So that's idle time for 1 day. It's sitting there waiting for this first server to be done. Once it's done, then it can process 2 for 4 days. So now the flow time of D is 19 days. But the flow time of the last job in the schedule is the total processing time. So the time of completion, 19 days. Total processing time, 19 days. Make span, 19 days. So we can see that from the Gantt chart. So from the Gantt chart, notice what I've identified. We can tell what the flow is of each job. We can tell the queue time in each job in front of the first server, second server. We can tell the processing time of each job by adding these up. 4 plus 1 is 5. We can tell the total processing time of the entire schedule of the project. And we can tell the idle time. Right here, 1. Well, notice 1 is going to not have will have no idle time until the very end. So the processing time of D after the first server is finished with processing A, B, C, D, notice there's no break, because that's going to be the flow on the first server, second job A on the first server, B, C, and D. So the flow of A, B, C, D on the first server is 15 days. And there's no break there. But once the first server is finished with A, B, C, and D, then it's waiting until the second server finishes with the last job in the schedule. So that time right there, so the total processing time is 19 days. Well, the total idle time of the first server is whatever the 19 is minus the flow here of 15. In other words, you take the flow on the first server, which is 15. Well, 19 minus 15 will be the total idle time of the first server in the total 19 days make span. Now for server 2, that's different. First of all, it's going to be idle at the very beginning. Let's shade that. And then it's continuous. Now right here, another time it's idle. Okay, so when this time here is greater than this time, you're going to have an idle time. Okay, and there it is. Now, when this time is greater than this time, you're going to have queue time. And we'll see that here. You'll see that in the homework, and which I will illustrate. So we can see a lot from the Gantt chart. Okay, now we can also use the progress report to actually analyze schedules. And down here, I've illustrated the Gantt chart for the Johnson's rule. And here we can see why the Johnson rule is the concept of Johnson rule. Remember the concept that the lowest times here will be on the first server, and the lowest times on the second, the smaller times on the first server is early in the schedule, and the smaller times on the last server will be later in the schedule. Okay, now we can see why that's true. In other words, if I take BDAC, when I look at this Johnson's rule, remember the total flow of the first server will always be 15, because that'll minimize the total flow on the first server. But once it's done on the first server, whatever time this is right here, the smaller this time, the smaller the total processing time of your project. And that's why the minimum times on the last server will be later in the schedule. Because if I had 6 here, well, this, for the first server, this will always be 15. But if I had B as the last one, well, then this is going to be 6 days here, and I'm going to go all the way to 21. But since I put 1 here at the last, then only 1 after I'm done here is just 16. The smaller times on the first server, well, the shorter times here will get the second server processing as soon as possible, because the value of an n/2 system is both servers working at the same time. So the shorter times here, then the faster the second server can start working. And that's why you want the shorter times first. Okay, so that's the Gantt chart. Well, that represents scheduling. A good introduction, a simple introduction, some very logical scheduling techniques that they're simple, but they're not obvious. A lot of people don't do these. And so if you do use them, you'll see that you'll greatly lower the processing time, create efficiencies much greater than just having FIFO or just random schedules. So you can greatly make your operations much more efficient. That's all I have. Between now and next time I see you, take care.